the space or antenna diversity we have already seen something like that when we talked about the electromagnetic ray reflected from the ground. So you remember we introduced antenna diversity and we said we can use two antennas to guarantee that our signal is not zero. But in that case, that situation was very different from this situation. Let me point out what the difference is. You already have seen antenna diversity in this situation, where you have a transmitting antenna. We have done an exercise on this. We have designed a system like this. But this case here was deterministic. We knew exactly the geometry of the situation. We knew exactly what were the distances, the antenna heights, and we just had only a direct path and a reflected path. In this situation, when we have multiple reflection, we are not in a deterministic scenario. We must calculate the distance between the antennas from a statistical point of view. We cannot be sure. In that case, we were sure that if we had 0 on one antenna, we had a perfectly constructed combination on the other antenna. That's why I'm saying it was deterministic. In this case, we can do the best that we can to maximize the probability that if we have a weak signal on one antenna, there is a stronger signal on another antenna. But we cannot be sure, because we have too many electromagnetic rays coming from too many directions, and the geometry is not well known. Okay, so there is a strong difference between the two situations. So the technique is the same, but the result will be different. So how do we design in this case? We need what we call spatial correlation. And how we do obtain this? Let's assume that on this axis we have position. Let's call this x. And here we have received signal. This will be a complex number because there is amplitude and phase. I cannot draw real and imaginary part, but you know that it is complex. So when we move around the place, for example, inside, along the street, this can be meters along the street. We found a signal that is fluctuating in space, like we found in this picture. Okay, so I'm drawing exactly the same thing. This is the position along the street of the unit, and that's a signal that we receive. So we take 2 points. Let's call this point x1 or p1, point 1, and this is point 2. We want to know how correlated are the signal between those 2 points. To do this, we can calculate the autocorrelation function of this in the standard way. That is, we define a function d of p1 and p2. This is the standard autocorrelation definition of a function. As if the receiving signal, let's call this voltage, so this is V. So at this point we will have, let's say, voltage V in V1, and here we have voltage in V2. So you define the function as voltage at the antenna connector, for example, in point V1 times the compressed conjugate of the voltage in point V2. Then you calculate the average value of this function. I repeat, I'm just reporting the standard definition of autocorrelation. Nothing special, just focused on our example. And if we discover that this is a function not of P1 and P2, but only on the distance between P1 and P2, so the value of that function does not depend on P1 and P2, but only on their respective distance. You see that in this case, you see that the process is ergodic. If you have done statistics, you say the process is ergodic and stationary. If the correlation depends only on the distance of the points. And we call this quantity WR, autocorrelation, as a function of distance, where delta R is the distance between the two points. Where delta R is what I call distance between point 1 and point 2. This function is what I will call spatial autocorrelation function. And now we will soon attach a meaning to this autocorrelation. So we can be more focused. So let's plot that function. And now I'm inventing a possible shape for that autocorrelation function. But it can be something like that. So on this axis we have the absolute value of W, call it WR, delta. And this is delta R, that is distance between the 2 points. Being an autocorrelation, the maximum value will be equal to 1 for delta R equal to 0. This is intuitive in the sense that if the 2 points coincide, they will be perfectly correlated. The 2 measurements that you make in the same point, the 2 points that overlap, will be exactly the same. So That's the best, highest correlation that you can find. Then, what that curves tell you is that when you move those points farther away, they tend to decorrelate. The correlation, the autocorrelation, goes down. What's happening in one point is less and less correlated with what is happening in the other point. In other words, if you know what is happening in one point, the further away you go, since the correlation is going down, the less you know of what's happening in the other point. Okay. And at a certain point, you got a zero or very, very close to zero. It will never be exactly zero, but a very low value of correlation. When this value will be indicated like delta dc, that is coherence distance. This point is called coherence distance. If we have to give a definition of the coherence distance that explains what's happening, what's physically happening, the coherence distance is the maximum separation in space, means distance, usually, over which the propagation channel can be considered stable or no. In other words, if the 2 points are at a distance greater than the coherence distance, so points whose distance is greater than the coherence distance will be uncorrelated. That is, what is happening if the 2 points are separated in space by a distance that is greater than coherence distance? If you know what is happening in one point, you don't know what is happening in the other point. Okay? If you know what is happening in one point, you don't know what is happening in the other point. They are completely uncorrelated. So this gives you an indication of at what distance you have to place 2 antennas. If you want to implement an antenna diversity, that is, you want to use 2 antennas to compensate for a destructive combination, at which distance you will place the antennas? Smaller or larger than the coherence distance? Smaller? Any options? Are there options? Why smaller? If the distance is smaller, you can be sure that if on antenna 1 you have no signal, on antenna 2 you have no signal, because the 2 things are very correlated. Your antenna must be placed at distances greater than the coherence distance. Because what you really don't want to happen is that you have 0 on both antennas. So if you place the antennas at greater, they will be uncorrelated. You are not sure that if you have 0 on one antenna, you have signal on the other antenna, like in this case. But it is very unlikely, since they are not correlated, that you have 0 on both antennas simultaneously. We will see that you know that the probability of uncorrelated events is the product of probability. So if you have 10% of probability, we will do exercises, but if you have 10% probability that something bad happens, if you have 2 uncorrelated antennas, this probability goes down to 1%, because it's 10% times 10%. Okay? Questions? Questions, please? So, antennas. If you use more than one antenna must be placed at distances greater of the coherence distance. And now we have to calculate the coherence distance. What it depends on? Let's focus just on what we are interested into. Mobile cell phone or mobile communication in general. But we are mainly on the geometry that we saw before. Base station on top of a building, users on the ground. Station on top of the building, and now a user on the ground. Okay, what we will find in a moment is that the situation is very different for base stations and for users on the ground. In particular, where are located the reflective objects, all the objects that give rise to reflected electromagnetic rays, where are they located? They are usually located all around the user. So users usually have reflecting, let me call them reflecting, but can be also diffracting, so that is not important. This means that the multiple electromagnetic rays at the user arrive from all possible directions. As you see in this example, he gets one electromagnetic ray from the base station arriving in front of him, and he gets a reflected electromagnetic ray coming from behind him. And maybe also he gets some side electromagnetic rays from nearby buildings. So in general, we can say that the electromagnetic rays can be considered direction of arrival of the electromagnetic rays for the users this direction of arrival can be considered to be uniformly distributed between 0 and 2p, all possible directions. This is a very simple analytical case because it's treatable in the sense that you can do a math calculation for this. If you assume that direction of arrival of those electromagnetic waves is uniformly distributed around the user, you can derive an analytical expression of the autocorrelation function that is pretty simple, apart from the usual function that you don't know because you have used it before. J0 squared L is the distance normalized, L divided by lambda is the distance normalized to the wavelength. And J0 of x is the usual Lagrange function. In particular, this is the zero-order Bessel function. J0 is the zero-order Bessel function. Of the first guy. The one that we have seen before is the modified function. This is the unmodified Bessel function. Again, you can plot it in MATLAB, and if you do that exercise, if you take this equation and you plot it, you'll find something that is interesting. Okay. I'll show you in a moment. Yeah, that's the plot I did in MATLAB. This is the distance, this is the cross correlation, and this is the distance as a fraction of lambda. So it's distance divided by wavelength on the mobile user, on the mobile terminal. And you see that the cross correlation goes down very quickly, and already at half a wavelength away, the signals are completely uncorrelated. Now, if we're talking about 900 megahertz, for example, that is the lowest GSM band. 900 megahertz is a wavelength of 33 centimeters. So, you can space two antennas at 15 centimeters on the mobile terminal, and they will be very effective because they will be uncorrelated. That's what you do, for example, on portable devices. You put two antennas on the opposite side of the chassis. Or on a car, there used to be two antennas to make diversity. But anyway, if you are the user on the ground, life is simple because the correlation distance is very small. So it's very easy to implement an effective antenna diversity system. Life is much more complicated for the base station. I will talk about the base station now, but there are questions? Is it clear what I'm talking about? Now, base stations. Life for base station is more complicated, but then at base station, a As you can see from the picture, from the drawing, the situation is very different. That is, the electromagnetic rays come from the location of the user, mainly. So the angles, the spread of the arrival, angles of arrival is much narrower. So we can say that the distribution of the angles of arrival is much narrower than the distribution of the user. The user is uniformly distributed over 360 degrees. On base stations, you usually find a value that is reasonable value that is between 10 and 20 degrees. So you can assume typical value of this distribution, 10 degrees. We call this angle distribution. And you can see this because those directions are very close to each other. So this angle here will be very small. So if you calculate the autocorrelation function for this kind of very narrow aperture of direction of arrivals, 10, 20, 30, 40 degrees. The equation that you find is much more complicated than this. But it's interesting to see the result. This result is the cross correlation as a function of distance in wavelengths, number of wavelengths. Here we had, in the case before, we had fraction of a wavelength because this was one wavelength. It was two wavelengths. In this case, we are talking 10, 20, 30, 40 wavelengths. This is a function you cannot read it because let me see if you have this graphic, but let me see if I can lock this thing down. All those curves refer to different angle distributions, and you see that the larger the angle distribution, the lower the correlation. So if you take a given value of distance or a given value of correlation, you will need a very large spacing for angle distribution of 5 degrees. And if the angle distribution is larger, then the correlation, the distance required to achieve a given value of correlation is lower. So if we take a typical value for a base station of 10 degrees, depends on your geometry, but it's reasonable to have 10 degrees. We have this curve here. Let me see what it is. This one. So at what distance would you place your antennas on a base station? Let's say that you are happy with 0.2 of correlation. You cannot be too picky to choose it, because otherwise we should put our antennas too far away. But let's say that we are happy with 0.2 of the cross correlation. You will have to put your antennas at 20 lambda. of distance. And at 900 megahertz, this is 6 meters of distance. And you have seen this before dozens of times. Because when you look at base stations, this is a classical 3-sector base station. Those two antennas are distant several meters, 5 or 6 meters. Those are the antennas that are needed for antenna diversity and reception. That distance on a mobile terminal becomes 15 centimeters because of the difference in angle spread. Obviously, those were the very first implementations. Now they are more effective. Let's say, less ugly communication towers where you use different countermeasures. But if you have to use space diversity on a base station, you have to separate the antennas by a large amount. Now, why is this? What is the physical reason for this terrible difference in distance? Obviously, the reason is the angles, but you can see that if you have, let me draw two limit situations to explain why this is happening. Imagine that you have here your user, and you have one direct electromagnetic ray here, and another one reflected coming from there. If you move a little bit from here, if you move of lambda over 4, the phase of this will be delayed and the phase of this will be anticipated. So you go from a completely destructive situation to a completely constructive situation. Let me see if I can, I'm not sure I'm able to do that. Let me see. No, I'm not sure I can do that. No. Don't ask me to do this, it's too complicated for my skills. But if in this point those are opposite in phase, if you move by a very small amount, the two electromagnetic rays will be in positive combination, because in this point, suppose that you have this situation. They are equal and opposite. If you move a little bit, this will rotate clockwise because this is delay. This will rotate on the other direction. As you end up, you move a little bit, you move by a quarter wavelength, and you find in this other point, you find perfectly constructed combination. Then you move a little bit and they will be opposite again. Let me use different colors. You can try this at home as an exercise, but I'm just... Okay, so if this is this, after a while, after quarter wavelength, they will be like this. So this is, let's say, position 0. This is position lambda over 4. And if you move to lambda over 2, the situation will be again destructive. But they change because one is rotating in one direction when you move, and another one is rotating the other direction, because this is delayed and this anticipates. Okay. But as far as the user on the ground is concerned, if you move a little bit, you can go from a completely destructive situation to a completely constructive situation. But if your electromagnetic rays, the directing and reflecting one, are perfectly now coming from the same direction, that is, this would be a situation where alpha, what that alpha that one called there is 0. If you have a destructive combination here, in this point, because they are like that, if you move of, say, a quarter wavelength, since they are rotating both in the same direction, because the direction of propagation is the same, if you move a little bit, you will find again, this is rotating like that, you will find again a destructive situation. This is 0, this is lambda. And if you go here, at lambda over 2, again you find always a perfectly destructive situation. So in this case, whatever the distance, we will always have 0 sigma. So, in other words, the phase correlation depends on the spread of the angles of arrival. The wider the spread of the angles of arrival, the smaller the correlation distance. Or on the contrary, the narrower the distribution of the spread of the angles, the bigger the coherence distance. That's why life is very hard on base stations and much easier for the users on the ground. This huge value of distance in some cases cannot be, is not acceptable, and then we have to think about other countermeasures. But we'll see those other countermeasures in the next lecture. Now I think we have a break.
Yeah.
Ready? I'm overdue, I'm sorry. We meet after the break for the exercises.
Good. Yeah.
Yo soy efectivo, gracias. Gracias.
So they are the same signals, but the amplitude in one point is completely uncorrelated with the amplitude. Just the amplitude. Yes, it's the correlation of the amplitude.